Great introduction. I'm very happy to have you giving this course on the non-Archimedean aspect.
Thanks for the invitation to speak here. So the goal for today is roughly to just give you an overview, or for a lot of you, maybe a reminder of what K-stability is. And along the way, I'll try to carefully actually follow through the original definitions so that we could see where we get these non-Archimedean aspects going into the picture. And then I think in the next 2 hours, Remy will do something more technical / important. Right, so the setup is the following. I'll always assume that X is a smooth projective variety over the complex numbers, and L is M1 bundle with some reasonably nice automorphism group, say discrete. Just to set up the notation, oftentimes I'll write R for the section ring of R. So this has a weight decomposition recording the C star action given by the line bundle along the fibers. So I think the notation I'll do is RM, where each of these RMs, the global sections of L. So this notion of K-stability really arises from this famous Yueqiao-Donaldson conjecture. And there are various generalizations to which you can state the conjecture, but I think the version that I'll work with is a uniform version for CSEK metrics. So the conjecture is that first term class of L admits a unique CSEK metric if and only if the pair is uniformly, or if you wish, just K-stable. At least for the purpose of this talk, it doesn't really matter if you have uniform or not. And in fact, a lot of things about the conjecture is already understood, especially in the Taylor-Einstein case. So I'll start by just trying to tell you what's already known about this conjecture, and then what's not known, what's remaining there. This is a little heavy for me, to be honest. So Taylor-Einstein case. They're divided into 3 different classes depending on the positivity of the Ricci curvature. So this is the equation, and up to normalization, you can assume lambda to be plus or minus 1, or just Ricci flat. Now, according to sort of the history, the first case that was resolved was the case when lambda equal to 0. And this is the Ricci flat case, and this is the Yell's theorem. Which says that in this case, there's always a unique Labial metric in the right class. And then Yell's method actually generalizes to the -1 case, or the canonically polarized case. So when lambda is -1, then you have the canonically polarized case. So this just means that L is canonical, and Alban and Yao has this result that, again, there's always a Taylor-Einstein metric in this C1 of Kx. And then there comes the third case, which is the Fano case. And this case is a little tricky because this type of theorem doesn't hold in general. This is when L is the anti-canonical. So in this case, a well-known example is going to be, so I guess this dates back to Matsushima, where he showed that in order for there to be a Taylor-Einstein metric, your automorphism group has to be sufficiently nice, reductive. So in particular, if you look at P2 blown up at point, this one does not have Taylor-Einstein metric. So this case is a little tricky. You need some if and only if condition for there to exist a Taylor-Einstein metric. And this is in fact true, but maybe before that, let me just say that in both of these two cases, K-stability is also verified, although much later, decades later, I guess, by Aldaka, 12 and 13. He showed that in both of these cases, you do get that this pair is K-stable, even when allowing some singularities. So in this Fano case, you would expect a theorem like this to hold, but this took much longer time and a lot of algebraic geometry input. So right now, you actually have the full theorem. At least the simpler version I'll state is due to, I guess, many people. Originally, Chen, Donaldson, Sun, and Pen. In the smooth case, via analytic methods. And then non-Archimedean geometry comes in, and there's a variational proof due to Berman, Boucksom-Jonsson, and later in singular case by Li. And then in this case, it's also known that this part doesn't really matter. Uniform K-stable is the same thing as K-stable. So this is relying on some finite generation result by Liu, Xu, and Zhuang. And Xu Zhuang has a different proof later. So the theorem just states that if there exists, I guess I'm going to start with the singular case, log Fano, then there exists a unique Taylor-Einstein metric in this case, if and only if it's uniformly K-stable, which is a priori stronger than K-stable, but it turns out that they're equivalent. Okay, so this is everything about the Taylor-Einstein case. Now, what's known about the general case is that there has been a lot of work by Li and also Boucksom-Jonsson. So in general, I guess one direction is supposed to be easier and relies maybe more on the analytic methods, and this is done by Berman, Darvas, Liu, and also Chen Cheng. That CSCK always implies K-stability. Now, going the other direction, you want to basically follow the same strategy, except that it's a little hard to just work with test configurations, and so that's when Li looked at K-stability, but not just testing test configurations, but also testing more generally filtrations. And he actually showed that this implies CSCK. I guess more precisely, he showed that it's the energy functionals satisfy this coercivity conditions. And so then through the variational approach, it implies CSK. And sort of the missing part is a purely algebro-geometric statement saying that this a priori more general K-stability notion is equivalent to the original one using test configurations. So K-stability for filtrations, whether this actually implies, sorry, the other way around.
I guess both of these are uniform because F3 has an example of a K-stable variety that's not uniform K-stable.
Yeah, both of these are uniform. Yeah. And as it turned out that the divisorial stability that we're going into is equivalent to this. Okay, right. So this is roughly the picture that we have already understood and what's missing here. And I'm going to move on to really go into the basics of Non-Archimedean stuff and try to go through test configurations in a more detailed way. But before that, any other questions? I'm not an example person. I suppose if you really look through, I mean, these filtrations are a little hard to check. I mean, test configurations are already hard to check, but filtrations even more. So I really doubt it. I mean, if there are going to be examples, I'm going to expect divisorial stability is more in the direction of checking examples, but still, it seems pretty hard. It's just because even like you have to check when you have to only maybe check a finite, even like, this is not true, but even when it suffices to check a finite number of valuations, then it's the formula here is still kind of hard to check. Yeah. But yeah, you can always play around with toric stuff. Yeah. Okay. Right. So some very basic definitions about Archimedean geometry. Really, I'm only going to need the definition for valuations and log discrepancies, and I'll restrict myself to divisorial valuations. So if you're a quasi-monomial guy, I'm sorry. But here's the definition, which is pretty much useless, but I thought it's good to know the original definition of a valuation before talking about the actual interesting divisorial ones. So real valuation on X is a map from the function field to R, so that the following is true. One is that V of F times G is the same as V of F plus V of G. And then you have the Non-Archimedean triangle inequality. And then the third restriction is that we're always going to work with the trivially valued field. So restricting to complex numbers. Non-zero complex numbers all have value 0, and V of 0 is infinity. So this is the formal definition of a valuation, and this is sort of the additive notation, and it's not very hard to check. Well, it's basically definitional that if you do something like e to the minus v, then you end up in a non-Archimedean norm. So all the same axioms except for this a priori stronger triangle inequality that is non-Archimedean. So the benefit of working with valuations in general is that this allows you to translate the information about test configurations back to the variety itself. But the space you're looking at is not going to be the original variety X. And instead, this Berkovich anticipation of X. So by this, I'll always mean this is the Berkovich anticipation of X with respect to the trivial valuation on the complex numbers. I'll do this. And as I said, it's nothing but the set of semi-valuations on X, meaning that there are valuations on sub-varieties of X. Yeah. Is the function field. Yeah. Yeah. I used too much K's. Function field. Yeah.
And
the third property is just saying it's trivial on complex numbers. So when evaluated at non-zero complex number, it's 0. Norm, yeah. On the function field. Right, so as I said, it's just the set of semi-valuations on X, which are valuations on sub-varieties of X. And the sort of the reason that we work with this space is that it has very nice properties that your original X had. So as a topological space, it's compact, Hausdorff. And also the space of valuations on X sits inside Xn as a dense subset. So it's a nice compactification of the objects that we're going to care about. And in fact, the important class in this set of valuations is the set of divisorial valuations. So in fact, you have such inclusions, and both inclusions are dense. So here, a divisorial valuation by definition is of the form a positive number times or E, where C is positive and E is a prime divisor over X. So you have a birational morphism from Y to X, and then E is a prime divisor inside Y.
what is the topology on this?
Yeah, I should have said that, sorry. So the topology, I'll just write it down. The topology is the weakest one, so that any maps induced by F in the function field, sending V to V of F as continuous. So it's kind of a weak topology, if you wish. Yeah.
I miss what Y one.
It's a birational morphism. And this is prime. Okay. And another thing that we're going to use, which sort of plays the role of canonical divisor in a way, is the log discrepancy function. So, and I'm only gonna define it for divisorial valuations because this is the only thing that we're gonna need. So log discrepancy, this is the notation for a divisorial valuation of this form is defined by, so again, I'm looking at this model, E sitting inside Y, so X is 1 plus the coefficient along E inside this relative canonical divisor. So I guess this is just this pi, then this is one. The pullback of the canonical divisor. So in a way, it's some sort of Jacobian if you wish. And in fact, you can extend this to all of Berkowitz space with values in 0 to infinity. And this is lower semi-continuous. Okay. So this is really all we need going into this non-Archimedean perspective of K-stability. And I'm now going to just carefully walk through the definition of test configurations again, and hopefully you won't find it very boring. Relation with test configurations. So these are the test objects for K-stability. K-stability is a notion saying that when testing through all possible test configurations, you get some invariant associated to each test configuration, and each of them is positive. Mission won't write much in words, but I'll just say all the test configurations I work with are ample and normal. And this is a flat family, X over A1, really XL with the polarization as well. And it's in GM equivariant isotrivial degeneration. So there's a GM action on the whole family, lifting the original action on A1. And this family is also proper and flat. It's the usual criterion for a meaningful family in algebraic geometry. But the important part is that away from the central fiber, it's GM equivariantly trivial. So in particular, I have an isomorphism for the fiber above 1 with the original pair you started with. So really, the only interesting that happens is over the central fiber. And this is where you get this Donaldson-Futaki invariant defined. So although Donaldson-Futaki invariant is a priori defined for the whole test configuration, but really the information is all restored in the central fiber. C star. Yeah. Right, so let me just write down a definition. K semi or stability is equivalent to asking that a certain Donaldson-Futaki invariant, which I'll define later using non-Archimedean point of view. But this is always, so semi-stability, you only need non-negative, but if you want stability, then you need positive for all non-trivial test configurations. Okay. So, the first step towards understanding K-stability is to really study these test configurations. And again, the information is restored in the central fiber. And this is where non-Archimedean geometry comes in, because once you have something in the central fiber, if you can sort of transform it into certain valuations, then you can get back to your original variety. And this is essentially how it goes. So the first important observation, which is actually not hard, originally due to, I think, with Nystrom and Siclidi, that you can think of this data as filtrations or later non-Archimedean norms. So you don't really have to work with the actual family. And this is already some of the more intrinsic data that is extracted from test configurations. So I guess I'd want to do a proposition. Yeah. So the set of ample test configurations is in one-to-one correspondence with, there's going to be some adjectives here, but z-valued, finally generated. I'll define in a minute along in the proof. Filtrations on the section ring R, which is also the same as z-valued non-Archimedean norms. Again, on the section ring. So a quick proof, omitting some of the details, is that to sort of go from test configurations to filtrations, you can sort of just exploit this GM action and define it in a way that so the filtration induced by test configurations lambda on each graded piece. So it turns out that these filtrations or non-Archimedean norms are sort of also invariant with respect to the C star action. So you just have to know what happens on each graded piece, and there's some compatibility that you have to satisfy. So I'm going to only define it for the graded pieces. But this is defined to be all the sections so that let's say our test configuration is given by proj of the section ring of X and L, maybe over A1, it's a relative thing, like so. Then you can, away from the central fiber, you can use the C star action to lift a section away from the central fiber to the total family, but again, away from the central fiber. And once you lift that, say this is the lifted section, and you can multiply it by t to the minus lambda and demand that this is still in the section ring of the total space. So this is how you go from test configurations to filtrations. I'll give a more precise formulation later once we really understand the central fiber. But for the moment, for this one-to-one correspondence, conversely, if you have a filtration on R that's nice enough, in particular finally generated, means the following, that the Riesz algebra associated with the filtration, which by definition is this bi-graded algebra over the polynomial ring in one variable. So you ask that this is finally generated over the polynomial ring. Then if you have this, then you can just cook up a projective variety by doing the relative proj. So in this case, the test configuration is recovered by doing the proj over of this Riesz algebra. Okay. So this is the first one-to-one correspondence. The second one is actually easier and definitional. Just have to sort of observe that. If you have a filtration, then you can define the non-Archimedean norm, which I'll denote by chi always, associated to the filtration. When you evaluate it at a section, say in Rm, then this is the supremum of lambda, so that S is in this filtered piece. And conversely, the filtration associated to a norm is going to be, RM. All the sections with norm at least lambda, sorry. So sort of a typical example. Yes.
For the non-archimedean norms, do you need finite generation to resolve?
Yeah. Yeah, thanks. So the typical example that we are going to care about, at least for today, is these norms or filtrations associated to valuations or divisorial valuations. Yeah. Yeah, that's why I didn't write it in the first place. But you can always, like through this correspondence, you can always translate to filtrations, and it's pretty much the same definition if you wish. Yeah. Right, this is on. If you have a sum of different graded pieces, it's the minimum of each of them. Yeah. Yeah, both of these things are on R. Yeah. So yeah. Example is you can take chi to be something associated to a valuation, say order vanishing along E as before, and then the corresponding filtration is going to be just in this case, order vanishing along E is at least lambda. Right. Yeah. Yeah. Everything is really on the section, right? Yeah. Or it satisfies the non-Archimedean triangle inequality. So when you add two sections, it's greater than or equal to the minimum of, yeah. Yeah, I'm gonna get to that if you can give me another 5 or 10 minutes. Yeah. Yeah, this kind of test configurations are very important. It's worth noting that these valuations are not always finally generated. Okay. All right. So yeah, maybe I'll just say it now, since you asked this question. So in this case, you can always still form the Riesz algebra as before, but the problem is that for a lot of the valuations, this Riesz algebra is not finally generated. So if it happens that this valuation is finally generated, meaning the corresponding filtration, when you form the Riesz algebra, it's finally generated, then it gives a test configuration, call it X, E maybe, such that in this case, it's very easy to write down the central fiber. And in particular, it has a very nice central fiber. So X naught is going to be the project of the associated gradient of the filtration. I mean, this is more generally true. You can always write down the central fiber as the project of the associated gradient associated to the test to the filtration induced by the test configuration, but you do in general get a scheme. It might have several irreducible components and might not be reduced. But in this case, if you have a degeneration given by valuations, then it's guaranteed that this is reduced and irreducible. So it's a variety in particular. And this is sort of, I don't know, commutative algebra exercise that the associated graded associated to filtration is an integral domain. So geometrically, it's reduced and irreducible if and only if f is coming from some valuation. And this point of view turns out to be very important if you want to talk about K-stability for Fano varieties, for example. But in general, you don't get this type of thing with irreducible and reduced central fiber. Okay, so this characterization of filtration, especially going from the test configuration, isn't very concrete. You do know there's a filtration, but it's not like it's still, you need to lift your section using this GM action, which in practice you wouldn't know how to do. So you would like something of this form, where if you start with a filtration that's described by maybe not one valuation, but several valuations, and you're hoping to get some description of the central fiber just by this sort of concrete construction, and vice versa. And so this is in practice what you do. It's really about extracting the irreducible components in the central fiber. So in general, what you do is the following. The central fiber, you can always write down its irreducible components with some reduced business as well. So B sub E is going to be the coefficient in front of E. This you can always do. And the observation here is that order of E sitting inside, so this E sitting inside the total space X as a test configuration is codimension 1. So this defines, in particular, a divisorial valuation on our test configuration. But our test configuration is birational to just the trivial family, X cross A1. So on the function field level, it's very easy to describe what a test configuration is, because the function field is just the function field of X adjoining a T. So in particular, once you have these divisorial valuations on the test configuration, you can restrict back to a valuation on your original variety X. And this is what you do. So B sub E is defined to be a suitably normalized restriction. So this just means restrict this valuation back to X. And this is a valuation, in fact, either divisorial or trivial on X. As long as you start with something divisorial. And you can also go backwards using the GM action. So you can actually sort of record all these GM action information by not lifting the sections, because that's harder. But if you can record it just using valuations, that's much easier, in fact. So conversely, so this is. I mean, we're looking at irreducible components in the central fiber, and it's an n-dimension, n+1 dimension family, because it's a relative family over A1. So this thing is a codimension 1 subvariety. Yeah, yeah. Oh, you mean this one?
Yeah.
I don't think it's hard as soon as you use this MBR current inequality thing. So it's a, yeah. Sorry, maybe I didn't understand the question. Yeah.
Like you start off with this, so I kind of
Yeah.
abstractly understand
Yeah.
the theorem that
Oh.
says that this is a divisorial
Right,
equation
right,
of X,
right.
but it's maybe hard to see that geometrically. To actually construct
Yeah.
a rational model Y of
Right.
X and put
Yeah. I'll describe you what the converse is, and I'll write down some bijection involving just valuations, and hopefully they'll be better. But otherwise, I don't have a much better answer to your question. So if you start with a divisorial valuation, you can reverse this procedure of restriction by doing certain things that's called a Gauss extension. And in fact, if you do the Gauss extension to this V sub E, you recover the original valuation sort of you start with. So these two procedures define the bijection. 1 plus 2 defines a bijection in between two spaces. One is you look at your test configuration and you look at the valuations on this, but GM equivariant. This is through this function field identification is the same as you just look at X cross A1 and maybe record all the GM invariant valuations. And this is a bijection with just valuations on X cross R. So specifically, the restriction goes this way, but if you start with a V and some number lambda, you can always do a Gauss type extension, but with maybe a parameter lambda. So more precisely, what you do here is, let's call it G lambda V, evaluated on some function inside this function field. And I want to do this weight decomposition so as to record the weights of the GM action. This by definition is going to be the minimum of, we need a little bit more space, V of F lambda plus, there's too much lambdas, plus 3 times lambda. So this one is when you take mu to be 1. So this is a sort of a perfect bijection in between the space of valuations on X and the space of valuations on test configurations by adding this GM equivariancy. And this is in fact true for much greater generality. Pretty much every time you have an algebraic variety with a torus action, you can decompose your evaluation space like this for some lower dimensional quotient, if you wish. Does that look better or worse? So once you have this, there's a perfectly concrete description of your filtration just using the central fiber, the irreducible components of the central fiber. So in this case, it's proposition / lemma that says that the filtration associated to a test configuration of Rm can be described as the intersection when you run through all irreducible components of the central fiber, and then you do something with the valuations induced by this E. E of S plus some constant. I think the constant is, yeah. Greater than lambda, where this D is the following. You have your test configuration, it's birational to X plus A1, but these two can be always dominated by a third one, say F and G. And this D is the difference between the pullback of L on this one and the pullback of the trivial line bundle on the trivial test configuration. So something like this. So this is a description of the test configuration using purely information on the central fiber, and this valuation correspondence sort of already encodes all the GM equivariants in this case. And in particular, if you write down the norm version of this, it's one of these divisorial norms. So the chi associated to this F is of the following form. Again, the minimum among all irreducible components, and then you first have the norm associated to this valuation, but then you need some other constants. Okay. So this is sort of where the non-Archimedean point of view started. And once you have this, you have to sort of understand these Donaldson-Fataki invariants in terms of valuations. And this amounts to having one, a variational perspective, and two, a lot of the times these intersection theoretic formulas help. I'll just go through that quickly because I don't think without going into too much detail, any of that makes sense. But I'll just at least say for the purpose of next two talks what the Mondra pair operator on test configurations are. So the upshot of doing all this is that you can rewrite Donaldson-Fataki invariant, but purely in terms of some sort of variational formula on the space of filtrations or the space of non-Archimedean norms. So I guess the theorem due to Boucksom is the model. Jonsson is that up to a base change. The Donaldson-Fataki invariant of the test configuration has this 10-10 type formula. So there's an entropy part, and then there is an energy part. Ricci energy and Mondra pair, where the entropy part is relatively easy to describe. Maybe I'll say that later, but the first thing is a Mondra pair operator to sort of go from, so now you have the space of norms or the space of filtrations, but this restriction is sort of still doing something to your norms. So this is encoded by this Mondra pair operator, which assigns, if you start with a test configuration, so this is sort of the notation for test configuration I'm using, you land up in some divisorial norm, which is a probability measure. So this sits inside the space of all random measures on Xn. This is the space. And this in particular is a probability measure. And the way to do this is, again, using the central fiber description. But if you start with a test configuration, then it assigns you a measure of the following form. The support is going to be on these sub e's, and the coefficients are intersection numbers. So with this, you can describe the entropy by integrating this measure. So entropy of a test configuration is going to be integrating over Xn of the log discrepancy function with respect to the measure, but you have a sum of the direct masses. So this is nothing but the sum over all irreducible components. And then you evaluate this section number, and then the log discrepancies, B sub E. The energy part is a little hard to write down, but yeah. What changes? This one? N is the dimension of X. Yeah. It's the top intersection number. Yeah. But I think I'll leave this part to Remy. But let me just say that it's some directional derivative along the canonical divisor of an energy of the associated measure. And somehow the point is this space a priori depends on the polarization, as it was asked before. But once you move on to the measure side, you can sort of have something that's independent of the polarization, and that is the point. Okay, right. So I was gonna do specifically an example here, maybe. Since I'm not defining anything, maybe I'll do an example. If you start with a divisorial valuation so a norm induced by a divisorial valuation, when you apply the Monge-Pair operator, of course, this is not necessarily finally generated, but either you assume it's finally generated or extend the operator to a larger class, which you might see next week. The associated measure is just the delta mass at V, and the norm, or this is not a norm, but the energy here of a delta mass at some, let's say, ord E, is the usual expected vanishing order, which is this integral over here, volume of L. It's an average of the sum of jumping numbers. So volume of, let's say, E is sitting over X via this birational map, and you want to pull back L minus T times E P. Where's the eraser? This looks like an improper integral, but it's actually a proper integral. And this is sort of the more algebro-geometric description of this. But in general, it could be harder to describe in purely algebro-geometric terms. Right. So what happens for Fano varieties? The whole theory for Fano varieties is very well understood by now, as of last year, maybe. So there was a lot of progress in the Fano case. Algebraic geometry, especially the minimal model program, was able to help it on. So, yeah.
What is the directional derivative?
So this is you vary the polarization here.
Okay, but in this particular example,
it's the same thing because L is KX.
so it counts.
Yeah, it's the same thing. Yeah.
Yeah.
Yeah, in the Fano case. Yeah. I assume you asked about the Fano case.
Yeah.
Yeah.
You're taking out yeah.
Exactly.
They should be minus.
Exactly. Yeah, there's some homogeneity conditions that could. Yeah. Yep. Exactly. So K-stability for Fanos relies on this very important theorem of Li and Xu, that it suffices to test special test configurations. This just means that your polarization of the test configuration is minus KX, and the central fiber is a KLT variety. So in particular, it's reduced and irreducible. And so you sort of end up in this easiest situation where you only have one irreducible component on the central fiber, and everything is by just looking at valuations. And in this case, for special test configurations, Donaldson-Pawtucket invariant has a much easier form. The entropy, again, no longer have like multiple components here. It just have one, which is the log discrepancy of the valuation associated to the central fiber. And the energy part, so that was a good question. It's just as, again, this valuation, because taking derivative along sort of the same direction does nothing by this homogeneity property. And in fact, with this definition, it's kind of easy to see, suppose you don't know any group theory, that this thing is not K-stable. All you have to do is to compute this criterion. So AX of the exceptional divisor E here minus S of E. This is in fact less than 0. And this is a very easy computation to do. And the problem with this is that, of course, once you have this, you want to say, oh, I just need to test valuations. But the problem, again, is that not all valuations are finally generated. Nevertheless, we do have this theorem by now due to many people, at least the version I'm writing down. Fujita, Aldaka, Zita Lee, Boucksom-Jonsson. So up to this part is about uniform K-stability if and only if this delta invariant of X defined as the infimum over all prime divisors over X. So over all divisorial valuations of A of E over S of E. And then you need some finite generation result. This is one. So I'll end by a quick proof of this. Now that you have basically all the machinery in the Fano case with all these finite generation results, it's actually not hard to prove. But I'm not saying any of these papers are easy. It's just after the fact proof. So one direction is easy. I think if you already know the valuative criterion, then it's K-stable by using Leishu's result. So if you already have this, then it's K-stable by. And the harder direction is you assume K-stable. You want to prove that you have this greater than 1, not only for finally generated valuations, but in fact for all divisorial valuations. Yeah, I think I'm missing maybe a paper here, but yeah. So the idea is to prove by contradiction, suppose to the contrary that delta is less than or equal to 1, then in fact there exists a valuation over X computing this delta. So is X over this, which we assume to be less than or equal to 1. And further, for valuations computing this delta, this finite generation result actually tells you that it's finally generated. So it does induce a special test configuration, destabilizing the original pair. And that's a contradiction. So, right, this is the sort of the full story of K-stability for Fanos, writing in a extremely brief way. But the takeaway from the understanding of K-stability of Fanos is that, in general, we're not expecting some Lie-Hsu type result for general polarizations. But you can still use this valuative point of view. It's just that you might need to incorporate several different divisorial variations in general. And this is exactly what divisorial stability does. And I think you'll hear more about it next week. Thanks.
I'm not getting the bigger picture. How does swapping one highly algebraic thing with another help with the final result that the K energy is coercive?
Yeah, this is through some not so easy computation about the sort of the. Sorry, am I understanding the question correct? Are you saying that how does this transformation help with the coercivity? Yeah.
Kindly speak.
Right. Yeah. Yeah.
And the test configurations in some sense are the algebraic geodesics.
Right.
Suppose we sort of can.
Yeah.
So replacing these test configurations by something very likely.
Yep.
Valuations, etc. How does that help with this analytic part?
So the actual point of view is that you can sort of think of there's a metric interpretation of these valuations as well as like positive non-Archimedean metrics on Berkowitz spaces and all such. And the whole point is that when you compute the usual K energy along the geodesic, if you compute the limit slope at infinity, you'll end up in these non-Archimedean functionals. So that's why we're like basically using the same name, because each Archimedean counterpart will, as you take everything to infinity and compute the limit slope, you'll end up in these things. Yeah.
Yeah, I have a question.
Yeah.
In part of those two main results that you wrote, do they also hold if you assume the automorphism is discrete?
Right, yeah. They also hold, except that you'll have to do something about this valuative criteria.
So
Yeah. Yeah, there's some delta T going on. Yeah. I guess for the purpose of like divisorial stability and so on, we're not going to involve this automorphism group business. Because from at least from the algebraic point of view, it's not so clear that if you have something K polystable, then your automorphism group is like reductive. It's true in the Fano case, but not obvious. Or yeah, already in the Fano case, it's a hard theorem from the algebraic side. Yeah.
So just a follow on, so what does break down?
You cannot form the test. Sorry, what was the?
So
It doesn't have finite automorphism group. So it's a little bit like these GIT type stability. Like you have K stable, but you also have like K polystable. You have to mod out the test configurations induced by the group actions. Yeah. Right. Yeah, there's delta T going on. Yeah, and it's the same greater than one condition. Yeah. Yeah, it's equivalent to K polystable. Yeah. Uh-huh. Yeah. So this is one. And this you can just so the canonical divisor is like 3h minus e. So you can just compute it using intersection numbers. It's in this case it's No, it's not. Well, no, because if you have a product test configuration, the central fiber restricted to the variety will be trivial evaluation. As long as you start with some non-trivial evaluation, it'll be
So
Yeah, so.
oh, this one is yeah.
Because
Oh,
E-
because E is the fixed point of the yeah. Yeah. I think you might get a non-product test configuration if you look at maybe P2 blown up at 2 points. I think there the destabilizing divisor is the transformation of the line through 2 points, or maybe that's yeah. Yeah. I mean, yeah. The only point I'm saying this is that no. The only point I'm saying this example is that the valuative criterion is actually very useful in deciding K-stability and stuff. Yeah. That's going to be infinity. Yeah, like really everything is defined on valuations, not yeah. Right. Yeah. Yes. Yeah. I guess the sort of the most slick way of saying this is to just take the greatest lower semi-continuous extension to Xn. But there are more like concrete descriptions for divisorial and quasi-monomial ones. In general, you have to take a limit. Yeah. Or a supremum. Yeah. Yeah. Thanks.